am absolutely thrilled to have you here today because we are going to look at, well, quite literally, one of the most mind-bending, awe-inspiring concepts in the entire universe. We're going to completely shatter the illusion that time is some sort of fixed, universal river, flowing at the exact same speed for everyone. Because the truth is so much stranger and honestly so much more beautiful than that. We are talking about time dilation.
So picture this. We've got two twins, Anjali and Rohan. Anjali decides to stay down at sea level, right at the foot of the Himalayas. But Rohan climbs all the way up to the summit of Mount Everest, and he decides to literally live up there for 5 years. Now, before they part ways, they synchronize two perfectly identical, incredibly precise atomic clocks. Fast forward 5 years, Rohan comes down the mountain, they put their clocks side by side, and guess what? They don't match. Rohan's clock is actually slightly ahead of Anjali's. No way, right?
Section 1. The Strange Nature of Time.
Okay, let's dive into this, because I know your very first instinct about those twins is probably to think, oh, the cold must have messed with the clock, or, it was just some sort of mechanical glitch. But the absolute physical reality is that time itself actually flowed at a different rate for Rohan than it did for Anjali. Crazy, right? To really grasp this, we basically have to unlearn everything Isaac Newton taught us centuries ago. See, Newton's view was that time was absolute. He thought 1 second on Earth was exactly the same as 1 second floating out in deep space. And I mean, that sounds obvious to our everyday experience. But then Albert Einstein comes along and drops this absolute bombshell. He revealed that time is relative. Space and time are actually woven together into this single, four-dimensional fabric we call space-time. And because of that, every single observer in the universe, you, me, everyone, we actually carry our own personal clock. And how that clock ticks depends entirely on where we are and how fast we're moving.
Section 2. Rule 1. Gravity slows time. So, that brings us to the first of nature's really weird rules governing time. It's a phenomenon called gravitational time dilation. Basically, it dictates how mass actually manipulates the flow of time. Imagine spacetime as this giant stretched-out rubber sheet. When you plop a massive object onto it, like the Earth, the sheet curves downward. It creates this dip, or a well. And that curvature, that's what we physically feel as gravity. Now here is the golden rule. Clocks sitting deeper inside that gravitational well tick slower than clocks that are farther away from the center. The stronger the gravity you're sitting in, the slower your time flows compared to someone hanging out in weaker gravity.
And this brilliantly illustrates exactly what happened to our twins in the mountains. Think about it. Rohan was up at the summit of Everest, nearly 9 kilometers above sea level. Because he was so high up, he was slightly further away from the center of the Earth's mass, so the gravity he experienced was ever so slightly weaker than the gravity Anjali experienced down at sea level. And because Rohan was in weaker gravity, his time literally ran just a tiny bit faster. Over the course of 5 years, Rohan actually gained about 150 microseconds. Now sure, that might sound totally insignificant to us, but for atomic clocks, and well, for the universe itself, it is an absolute undeniable reality.
Section 3. Rule 2. Speed slows time.
But here's the thing. Gravity is only half the story. Time dilation isn't just triggered by the sheer mass of a giant planet. It's also triggered by velocity, how fast an object is moving through space. To understand velocity time dilation, we do have to gently introduce a little bit of the underlying math. But don't worry, it's actually super elegant. It's called the Lorentz factor, and we represent it with the Greek letter gamma. This mathematical key basically calculates exactly how much time slows down for an observer moving through space compared to a stationary observer who's just watching them. The basic rule of thumb is this: the moving observer always experiences less time. Their clock gets stretched out.
Let me just guide you through what we're looking at here. At the kind of speeds we travel in everyday life, walking, driving a car, even flying in a commercial jet, the Lorentz factor is basically just 1. The time dilation effect is virtually 0. You don't even notice it. But as you accelerate and actually start to approach the speed of light, look at how that curve behaves. Gamma just shoots straight upward. At 86% the speed of light, time slows down by a factor of 2. And as you push to 99% or 99.9%, time just stretches boundlessly. The faster you move, the slower your clock ticks relative to the rest of the universe.
Now, if you're sitting there thinking this is just some theoretical whiteboard math, well, here is undeniable real-world proof.
Way up high in Earth's atmosphere, like 15 kilometers above us, cosmic rays are constantly colliding with atoms, creating these subatomic particles called muons. The thing about a muon is it's highly unstable. If it were just sitting still, it would decay in a flash, just 2.2 microseconds. Even if it was traveling at 99% the speed of light, it should only make it about 660 meters before completely decaying. It should literally never reach the ground. And yet, we detect millions of them hitting the Earth's surface every single day. How is that possible? It's because they are traveling so incredibly fast that their internal clocks actually slow down by a factor of 7 compared to our clocks down here on Earth. Relativity is literally what allows them to survive that 15-kilometer journey. Nature itself is basically running a 24/7 relativity experiment right over our heads.
Section 4. The famous twin paradox.
We are now going to push velocity time dilation to the absolute limit. Let's bring back our twins, Anjali and Rohan. They're both 32 years old now. This time, Anjali is going to stay on Earth, and Rohan is boarding a ridiculously fast spacecraft capable of traveling at 86.6% the speed of light. His destination? A star exactly 5 light-years away. At year 0, they wave goodbye. Now, because Rohan is moving so incredibly fast, his time is flowing at exactly half the rate of Anjali's. So when 5 whole years pass on Earth, Rohan reaches the star, but he has personally only aged 2.5 years.
Now notice the critical turnaround point in the middle of this journey. This is super important because this is exactly where the quote-unquote paradox is solved. When Rohan reaches that star, he has to turn around to come back, right? To do that, he has to physically decelerate, stop entirely, and then accelerate back toward Earth. Anjali, she never accelerates. She just stays in her exact same frame of reference on Earth the entire time. That intense deceleration and acceleration completely breaks the physical symmetry between them. Rohan's change in speed means he is unambiguously the traveler in this scenario. So he flies back, another 5 Earth years pass, but only another 2.5 years pass for him. When they finally reunite, Anjali is 42 years old. But Rohan? He is only 37. He is literally, physically, biologically 5 years younger than his twin sister.
Section 5. Relativity in your pocket.
All right, it's super easy to look at that and say, wow, okay, really cool sci-fi story, but what does any of that have to do with me? Well, let's bring this explainer crashing right back down to Earth. I want to highlight exactly why this matters to your daily life right this very second. Look at the Global Positioning System, GPS. We've got these satellites orbiting 20,000 kilometers above our heads, constantly broadcasting incredibly precise timestamps right to your smartphone. But those satellites are caught in this crazy relativistic balancing act. Because they're so far away from Earth, they experience much weaker gravity, which actually makes their atomic clocks gain about 45.9 microseconds a day. But they are also orbiting super fast, like 14,000 kilometers per hour fast, which makes their clocks lose about 7.2 microseconds a day. When you combine both of Einstein's rules, those satellites experience a net gain of 38.7 microseconds every single day compared to us down on the ground.
So the absolutely crucial point here is this. If engineers didn't program the GPS computers to deliberately correct for Einstein's theories, those timestamps would start drifting. And because light travels so unbelievably fast, an uncorrected error of just 38.7 microseconds would mean your smartphone navigation would be off by 11.6 kilometers every single day. Seriously, within just a few hours, Google Maps or Apple Maps would be completely useless. So Einstein's equations aren't just some abstract physics concepts, they are literally steering your car.
Section 6. Speed through spacetime.
Okay, we are arriving at the grand finale. Here is the deepest, most philosophical insight of this entire explainer. Einstein realized that absolutely everything in the universe moves through the combined fabric of spacetime at exactly the same total speed, the speed of light. Let that sink in. If you are sitting totally still in your chair right now, 100% of your movement is directed through time. You are aging at the maximum possible rate. But if you stand up and start running, or, jump into a rocket ship, you are taking some of that motion and redirecting it through space. Because your total speed through spacetime is fixed, moving faster through space literally leaves less speed for time. You actually slow down in time to speed up in space. It's like a cosmic speed limit.
And this brings us to the ultimate mind-bending conclusion of these mechanics. Think about a photon, a particle of light. A photon travels through space at exactly 100% the speed of light. Therefore, it has absolutely zero motion left over to travel through time. For a photon of light, time effectively stops. It simply does not experience duration. If a photon is emitted from some distant star across the galaxy and it travels for 1,000,000 years just to hit your eye, well, from our perspective, yeah, it took 1,000,000 years. But from the photon's perspective, emission and absorption happened in the exact same instantaneous moment.
Which leaves us with this final profound thought. Einstein didn't just tweak a few math equations, He completely redefined our reality. We are all moving through this fluid, flexible universe where time actually bends to speed and gravity. Your now is uniquely your own. Like he said, time does not pass equally for everyone. Nature never promised that it would. So, the next time you look up at the night sky, ask yourself, are you seeing ancient history, or are you locking eyes with a photon that has experienced absolutely no time at all?